In this video, I'm going to show you how to find the components of a given vector. So we want to find the components of this vector A if it makes an angle of 60 degrees with the positive x-axis and has magnitude 10. Okay, so first let's draw a rough sketch. So let's just eyeball about 60 degrees from the positive x-axis. We'll make that vector A run that way. Let's go ahead and label our angle. This is going to be 60 degrees, and we'll also label our magnitude. The length of the vector is 10. Alright, so we want to find the components of A. That just means we want to express A as a vector consisting of two components. First of all, there's the x component, AX, and then there's the y component, AY. So let's draw that in on our graph here. AX is the x component, so that's the part of the vector that's going horizontal, parallel to the x-axis there. So that has a length AX. And then AY is going vertical, parallel to the y-axis. So let's put that right over here. So this will be AY. Okay, so now it just remains to solve for AX and AY, and we can do that using this triangle. This triangle is a right triangle, so we can use some trig ratios here. Why don't we start off with solving for AX? So what relates AX to 10? Well, AX is the side that's adjacent to this angle, and 10 is the hypotenuse, so we can use cosine. Cosine of 60 degrees is equal to adjacent, which is AX, over hypotenuse, which is 10. So we can go ahead and solve that, multiplying both sides by 10. We get 10 cosine of 60 degrees is equal to AX, and cosine of 60 degrees, that is just a half, so 10 times a half is equal to AX. So 5 is AX, and let's go ahead and fill in that coordinates there. So A is 5 for that first coordinate, and then it just remains to find AY. So AY, you can probably guess we're going to do that in a similar way. So looking at this angle, AY is the opposite angle, so we want opposite and hypotenuse. What gives us that? Well, that's just sine of 60 degrees will give us that opposite AY over the hypotenuse, which we know is 10. And then we just go ahead and solve. So multiplying both sides by 10 again, we've got 10 sine of 60 degrees equals AY. And then simplifying, sine of 60 degrees is just root 3 over 2. That's equal to AY. So cancel out the 10 and 2. That turns into a 5. So just 5 root 3 is AY. So let's go ahead and fill that in here. 5 root 3, and there we go. There are the components of A. Great, so now that we've done a concrete example, let's look back at our work and write down a general formula. So in particular, look at this line here. AX is equal to 10 cos 60 degrees. In general, we can write that AX is equal to, so 10 was the magnitude of A, so AX is equal to magnitude of A times cosine of the angle. Angle was 60 degrees, so cos theta. All right, and then by the same reasoning for AY here, we can write that AY is equal to magnitude of A, then times sine of our angle. And there we go. So these are our two formulas that we're going to be using to compute the components of a vector if we're given the magnitude and an angle. All right, here's another example. So it's the same idea. We want to find the components of this vector v if it makes an angle. Theta is 4 pi over 5 with the positive x-axis and has a magnitude of 5. So let's start out by sketching that. So theta is 4 pi over 5, so that is almost to pi, so looking something like this roughly. So that'll be our vector v, and let's label the angle angle is 4 pi over 5. And let's also label the magnitude. The magnitude we're given, that is just 5. Okay, so again, we want to write v in the form of components. So that just consists of the two components. There's vx, and then there's also vy. And we know from the previous example that our formulas to compute vx and vy, given the magnitude and the angle, are vx equals magnitude times cos theta, and then vy is magnitude times sine theta. So let's just go ahead and compute these. So sticking in the magnitude here, magnitude is 5, so 5 cosine theta is 4 pi over 5, and now we just have to compute this. This isn't one of those nice angles. We have to use a calculator for this one, so make sure you're in radian mode and just punch this in, and you should get rounded to do decimal places, negative 4.04. So that's approximately equal to that. And it's the same idea to get vy, that's magnitude times sine theta. So same as before, but now instead of cosine, we have sine of 4 pi over 5, and that is approximately, using our calculator, 2.94. Okay, so now we just have to put them into the component form. So let's write that over here. Vx is approximately negative 4.04, and then Vy is approximately 2.94. Just to show that approximately, let's turn this into an approximate sign, and there we go. That is the component form, approximately. All right, next example. So we want to find the components of the vector r if it makes an angle theta, which is negative 15 degrees with the positive x-axis, and has a magnitude of 7. Okay, so this is kind of like before, but now we have a negative angle. Okay, so that just means we go backwards. We go clockwise instead of counterclockwise. And then we just stick that in our formula. Everything is the same as we've been doing. So let's just go ahead and write this out. So r, we want to put that in component form. Components consist of rx, the x component, and ry, the y component. And then to find the x and y components, we just plug those into our formula. So plug the magnitude in, magnitude is 7, and then cos of theta is negative 15 degrees, and then we just punch that in our calculator. Now we're in degree mode, be careful of that, and the result is approximately 6.76, and then same idea for ry. Ry is sine, so 7 sine of negative 15 degrees, and that is approximately equal to negative 1.81. Okay, so that's our components. We just put that into our component form here. Our x is just 6.76, and our y is just negative 1.81, and there we go. So that is approximately our component form for r. All right, here's a final example. So we want to find the components of this vector b if it makes an angle theta naught of pi over 7 with the positive y-axis this time. So not the positive x-axis, the positive y-axis. And it has magnitude of 3. Okay, so we've got a diagram here. It's not the positive x-axis, it's the positive y-axis. But in order to use our formulas here, we still need to find the angle it makes with the positive x-axis. All right, so how should we do that? We want to find what is this full angle here, and we only have that part of the angle. But we know that this here is a right angle, so we can just add to find that. So this full angle theta is just going to be that's just going to be a right angle pi over 2 plus the bit of angle we're given here, pi over 7. And let's go ahead and add that. So how about turn them both into over 14? Pi over 2 is just 7 pi over 14. And then pi over 7 is just 2 pi over 14. Add them, you get 9 pi over 14. So that is what we're going to be plugging into our formula here. Okay, so bx, the x component, is the magnitude of b, which is 3, then times cosine of our angle. Our angle is just 9 pi over 14, and that is approximately equal to negative 1.30. The y component is similar. We're just using sine instead of cosine, so 3 sine of 9 pi over 14, and that is approximately equal to 2.70. Okay, so now we can write b in component form. So b is approximately equal to the x component of negative 1.30 and the y component of 2.70. And there we go. There is our final answer. Now we're pretty comfortable finding the components of vectors in 2 dimensions, and in the future we'll also learn how to extend this technique to find the components of vectors in 3 dimensions.